This work proposes a new loss function and mix-up technique for image retrieval with deep networks. Given a query image, we want to retrieve relevant samples from a large collection. We focus on training a network that generates an embedding vector per image. Then, embedding similarities between the query and each collection sample is used to perform the ranking and obtain retrieval results. Popular hand-designed loss functions, such as contrastive and triplet, pulls the sample from the same class together and pushes the sample from different classes apart. Instead, we focus on optimizing recall at k, which is a standard retrieval evaluation metric. To compute it, we first need the similarities, and then we sort the collection samples. And then we count the number of samples that have a rank lower than k. Recall at k is non-differentiable, therefore it is not applicable for training. Let's deconstruct its computation and see what the problem is. We need to estimate the rank of positive samples, such as the sample shown in green. First, the similarities of this positive is subtracted from each similarity of the other collection samples. Then the difference of the similarities is passed through a step function. Output equal to 1 indicates an example rank before the green example. Therefore, summing these values provides its rank, which in this case is 3. The same process is repeated for every positive in the collection to obtain their ranks. We then subtract each rank of positives from the value of k. Let's say k is 2 for this case. We pass these differences to a step function, and the output indicates if the rank is lower than k or not. And we sum up these values to count the number of positives that have a rank lower than k. The ratio of this count over k is equal to the value of recall at k. Recall at k is non-differentiable due to the use of two step functions. To obtain a differentiable approximation of recall at k, we replace the step functions with appropriate temperature control sigmoids. A steep sigmoid results in good approximation, but sparse gradients, which is not useful for training. A proper balance and trade-off between the recall approximation and gradient sparsity is needed. Now, let's see how the batch is constructed during the training. We follow class balance sampling and sample m examples for n classes. Then pairwise similarities are computed. Each sample is used as a query. Samples from the same class as the query are positives and the rest are negatives. Similarities needed for recall at k surrogate estimation are already available. This brings us to the second contribution of our work, which is on Mixup. Two embeddings of samples from the same class are mixed by linear combination to form a synthetic embedding. We repeat the same for all the samples with random mixing coefficients. Unlike other approaches, we do not renormalize the resulting embeddings. Now, the training batch constitutes of the original and the synthetic embeddings. And all the pairwise similarities are then computed. So that for any query, the required similarities are already available for the loss computation. It turns out that similarities involving synthetic embeddings are a function of similarities in the original batch. Therefore, embeddings are never explicitly mixed, but only the scalar similarities are efficiently mixed in our setup. Training with large batches is crucial for the proposed loss. We use the batch size of up to 4096 large resolution images on a single GPU. We follow the approach of Revolt et al. And publicly release the implementation. First, the first feed forward is performed in small batch chunks to obtain the embeddings. Embeddings are stored, but the intermediate features are discarded. In the second step, we compute the loss for each sample and store the gradients of the loss with respect to the embedding vectors. Finally, we perform second feed forward pass before we complete the full backward pass by using the stored embedding gradients. The synergy between the three aspects of our work, namely recall at k surrogate loss, similarity mixup, and training with large batches, lead to state-of-the-art results on 4 standard deep metric learning benchmarks for fine-grained recognition. We additionally show results on instance-level search, where our approach is consistently better than methods that use approximated average precision as the loss. Our implementation can be publicly found on GitHub. Thank you.